Hope my screen is visible. Can someone confirm on chat? Great. So since today is the first live session, we'll wait another 2-3 minutes because people typically tend to have some technical issues in joining and all that. Great that you guys have joined early and on time. But we'll just wait a couple of minutes before I get started because I don't want to have to repeat the same things. In the meantime, feel free to introduce yourselves on the chat box. So let me do that first. So I'm Prashanti. I'm a PhD student at the Indian Institute of Science, and I'll be the TA who handles the live sessions for this course. Yeah, so feel free to introduce yourselves. Tell me your name, what do you study or work on, and which institution / company you're affiliated with. Feel free to do that. No pressure. Yeah, people are still joining, so let's just wait for them to. Great. Hi, Shreyas. Anyone else? Great. Nice. Nice to meet you virtually, Venkatramana. Hi, Shivam. If anyone else would like to introduce themselves, please go ahead. We'll wait one more minute and then get started. Hi, Sushma. Nice to see there's such a diverse crowd, right? Hi, Saroj Kumar. Great. Great. Nice to meet you, Shivam. Anyone else? Okay, if not, for people who missed my introduction, I'm Prashanti. I'm a PhD candidate at the Indian Institute of Science, and I'll be the TA handling the live sessions for the GPU Architectures and Programming NPTEL course. And nice to meet you all. This is the very first live session we are having. So I'll take a couple of minutes to introduce this concept of the live sessions because I'm not sure how many of you have taken this before, how many of you are new to this. Okay, hi Divyank, nice to meet you. Great, nice to meet systems folks. I think people who take this course definitely have an interest in systems, so very nice to meet all of you. Great, I'll just wait for a few more seconds in case anyone else wants to introduce themselves. Okay, let's go ahead then. So, in terms of the live session, we will be having 1 2 hour session conducted every week. It would be at the same time every week. So, Monday 7 to 9 p.m. is the slot, and the Google Meet link will not change, but I think you keep getting reminder emails every week. So, you can just use that and join in. And what is the point of these sessions? They are supposed to help you solve your assignment questions and your exam questions better. Okay, looks like people are still joining. Yeah, one request from everyone, please join within a minute or two from the next session, because it's a bit of discontinuity for you guys also if you join 5 minutes late. And it's the same for me. I'm in the middle of a sentence and then I get lost a little. So yeah, that's something on the time side. But the main point of these sessions is to help you guys with the problem solving or with the application of the concepts that you learn in the course. So we'll be dealing with problems that are very similar to your assignment questions, but they won't be the same questions as the assignment, because obviously we want you guys to solve the current year's assignment questions on your own. But once the assignment deadline is over, if you have some doubts, we can discuss those in the live sessions. And we'll also take doubts from that week's course content. So for instance, today is the very first live session. So this is the week 1 live session. So I will be focusing on the week 1 course content and some problems based on that content. So make sure you ask all your questions or doubts or queries from that week's topics during this session. Next week, in our second live session, we will be focusing on the week 2's course content. Since we have 12 sessions and 12 weeks, this is kind of a nice way to divide the content, at least according to me. And it's easier for you guys as well, because some of you might have watched the week 3's content already, some of you might not have. So this way it kind of streamlines the process and everyone gets a chance to ask questions, right? And so I don't know how many people will be joining. So for now I've kept only the chat box on. In case we have very few people, say less than 10, I'm open to enabling mic in case you guys want to speak up. But typically if it's more than 20 people, it gets very chaotic to manage people randomly unmuting themselves and turning on their video. So I've kept the chat box for all your questions, discussions, doubts and things like that. And post the session, you will get access to both the slides and the recording. The recording would be posted on YouTube and the link would be shared with all of you guys. So don't worry in case you have network issues and drop off or something like that. But do attend these sessions. Don't think I'll watch them on YouTube, because the whole point of it is to have some interaction. Right? You already have recorded course material as part of your course videos. So the point of having these live sessions is to get your questions answered live by someone. So make sure you attend them, and I tend to make them as useful and as interesting as I can. So coming to how we will, since this is 2 hours, so yeah, first of all, it's a 2-hour live session, which I think is being done for the first time. So up to the last iteration of the course, it was 1 hour session per week. So 2 hours is a lot longer than that. So I totally understand if you guys also find it difficult to focus the entire 2 hours. So we'll see how it goes. Since today is the first session, I've come with a certain structure in mind. Depending on how this goes, if you guys have any feedback or anything you'd like me to introduce, feel free to share that at the end of the session. So before I close the session, I'll ask you guys how you thought the session was and if you'd like to see any changes, right? And depending on that, the next time I will make changes accordingly, because the whole point of this live session is to benefit you guys. So today this is how we'll do things. We'll spend 20 minutes on a very quick recap of that week's course content, just to see if you have doubts or questions and just to brush up the fundamental concepts of that were covered. Again, this won't be like a very detailed recap where we go through each and every slide, because I'm sure you guys have already done that when you watched the recordings. And we will spend the bulk of our live session, around 1 hour, on problem solving. So like I said, these will be questions very similar to your assignment questions. and we will do them interactively, right? It's not going to be a monologue where I read out the question and then I read out the answer and then I tell you this is how it's done. So I will actually give you time to solve questions. So if they are numerical questions, I will give 2 or 3 minutes or even more if someone would like extra time. So feel free to ask and have a pencil or pen or even a tablet, whatever you prefer to solve questions, right? But I expect the class to respond on chat. It's fine if you give a wrong answer, it's fine if you're confused about the question. All of those things are fine. This is not a place where you're judged or graded depending on your answers. So feel free to post an answer even if you're unsure about it or you have questions, it's not very clear. But please do respond, because when you ask me a doubt, that's when I realize that this is something that's not clear and I need to spend more time explaining this, right? And that helps me teach better. So please do interact and don't leave the session completely up to me. And we will have 30 minutes for doubts and any other questions that you guys have. And there is also a discussion forum. I'm not sure if you guys noticed. So as part of the NPTEL course page, I think there is a button saying ask a question, where it takes you to a Google group and then you can mail your question to the rest of the group. So we will also go through doubts that are posted there, although I think they've already been answered. So this is for folks who haven't seen those questions. And in future, if you would like me to address a particular portions, let's say you're watching the lecture and some part of it wasn't clear to you, so mention the slide number or mention the time at the time marker in the video and say this wasn't clear to me, could you please explain this in the live session? So that will help me also come prepared to spend more time on that, right? That's one way we can do. Or if you want to ask questions impromptu, that's also perfectly fine. I will try my best to answer them. On some questions, I might tell you that I'll get back to you next week. I'll note it down. I'll make sure to answer it the next time, right? Like I said, interaction is the main point of these sessions. So we'll keep it interactive. And since 2 hours is a long time, I will give maybe a 2-3 minute break once we hit the 8 o'clock mark. Feel free to get a coffee or a water or just walk around and come back. That's perfectly fine. I understand that 2 hours is a long time for people to focus on one thing. And feel free to ask anytime you feel like you need a couple of minutes. I'm okay waiting. And yeah, like I said, I'm open to the feedback. So with that, we'll get started. So before we get started, does anyone have questions on the logistics? I'll wait 30 seconds. If you have any questions on the live sessions itself, feel free to ask. Questions, comments, suggestions, anything that you'd like. Okay, if there's nothing, let's get started. So, like I said, today we'll be focusing on the topics covered in week 1. So, week 1 was, okay, someone is just joining. Great. So for people who join late, these slides will be available later on Drive. You will get a link to access them. So feel free to go look it up. I won't repeat things I just said because I don't want to bore people who've been listening from 6 o'clock, right? So today we'll be looking at everything that was covered in week 1, which is basically a review of your ComPark, right? So we looked at things like the 5-stage pipeline, the memory hierarchy, CISC versus RISC, data path, pipelining, some hazards that you encounter when you try to do instruction level parallelism. Then we looked at caching. We briefly looked at locality in terms of spatial and temporal. And then we discussed the various cache mapping policies, right? Direct, set associative, and things like that. And then we also looked at cache replacement, branch prediction. I think we started off with a naive predictor and then worked to build complexity. And we also looked at some register renaming methods as to how to address some of the hazards that you see. So this first 15-20 minutes we will be looking at a very short recap on the basic concepts that we have, right? And if you have any other questions on whatever I'm talking about right now, feel free to ask me. So a basic stage of stage is so this 5-stage pipeline, right? You would have, maybe if you've taken a even more basic undergrad course on Compark, you might have heard of a 3-stage pipeline. But this is kind of the standard 5-stage pipeline that you have, where the 5 stages are fetch, decode, execute, memory, and write back. So fetch is where you fetch the instruction, and then decode, you're trying to understand the instruction semantics, and then you try to execute based on whatever you've decoded, right? And there could be various types of instructions like arithmetic, logical, memory address, or a branch condition computation. And similarly, after that you have the memory and the write back stages. So now this might seem very basic to some of you guys who are familiar with the 5-stage pipeline. So think about this, right? For instance, so I'll ask some of these open questions. Feel free to think about them and come back to me maybe in the next session if you have answers, or feel free to post answers if you can think about them right now. So let's say I have RISC instructions versus CISC instructions, right? And can you think of something? Okay, people are still joining. Yeah, from next time, please make sure that you join on time within 1 or 2 minutes so that it's easier for you guys as well. Right, so think of a RISC versus CISC architecture, right? Can you think of some of the disadvantages or some of the problems that you might have in one of these stages when that changes? For instance, if you, in one of these methods, right, if you have a large variety of instructions, then how would the decode change, or how complex would it become? These are some things that that actually matter in many ways, right? So if you think of modern day virtualization and virtual machines, there are a lot of techniques that, for instance, emulate from one instruction set to the other, or they do some kind of translation from one instruction set to the other. And in such cases, these factors do play a role. How the ISA itself, how the instruction set architecture itself is defined, plays a role in decoding instructions and things like that. So I'm just trying to tell you a little more than what you've already learned in the course, in case all of this is very basic. But in case you have a doubt on something in the slide itself, feel free to ask. So now that we've seen the 5 stages of execution, what one optimization that we could do, a basic optimization, is pipelining, right? So you have 5 stages and you operate these 5 stages in parallel for a bunch of instructions. So what's the idea behind doing this? It's basically that every stage that you see here is processing something. So if you go for a serial execution, what happens? Let's say you have instruction 1. Let's see if I can get a pen here. Okay, people are still joining. 1 second. Right, so you have, let's say you have, this is a non-pipelined execution, right? Let's say you have the first instruction. It goes through the fetch, then the decode, then the execute. Now let's think about this instruction in the execute stage. What about these 2 stages? Nothing is happening there, right? It's basically an idle sort of condition. So one optimization that you could do to overcome that is to pipeline. It's basically to say that while my instruction maybe I is executing in the execute stage, you also have another instruction that is in some other stage, and that's possible, usually possible, unless you have some hazards. So what's the advantage of doing this? You have one instruction that completes in every clock cycle, although that one instruction itself might take 5 clock cycles. So read this carefully. It just says that in every clock cycle, one instruction completes. It doesn't say that it takes one clock cycle for an instruction to complete. So there's a difference there that we'll be coming to in one of the questions. But this is something important to understand about pipelining. Okay, for people who joined and are a bit lost, please refer back to the slides. Meaning of hazard in pipeline. So I don't know if I have a slide on that, but you maybe let me share the let's see if I have the course slides themselves. This was discussed in the course. So basically there are a bunch of different types of hazards, right? For instance, structural hazards, and then control and data hazards. And it basically means that you can't do this theoretical sort of pipelining that I just spoke about, because there is some kind of a dependency. And maybe let's see if I can just stop sharing and reshare the course slides, but let me first see if I have that. No, I don't have that downloaded. So I would suggest you go back and look at the course material. And one instruction I have for everyone is, please look at the course material in advance. And if you want me to focus on one particular slide, please also ask me in advance so that I have the slides ready and then I can talk about it. Okay, great. So let's move ahead. So I think you've looked at the memory hierarchy, right? So you have the CPU, and then the cache memory, and then the primary memory, and then the secondary memory. And drawing a parallel, if you have read the OS, if you've taken the OS course at some point in time, you would have also seen this picture. I think it's from Galvin. It was also there in the OS course in NPTEL. You would have seen this whole storage device hierarchy. So this is maybe a simplistic diagram. The way to think about this hierarchy is in terms of three things: the storage capacity, and the access time, and the volatility. So given any medium, how fast is that medium? How big is that medium? And is it volatile or non-volatile? Meaning, can it retain data after you power off, or will it lose data? That's volatility for you. And so this is kind of a detailed hierarchy where you have the same registers which are at the top of the hierarchy, and you can see this pyramid sort of thing. Yes, this is recorded, and you will have access to the recording on YouTube as well as the slides. So don't worry about it. You will get access to it. Right. So you start off from the registers, and then you have the cache, and then the main memory, and observe this pyramidal shape, right? Where the size keeps on increasing, but also observe the axis on the right. So the speed keeps on decreasing. So registers are much faster than cache, which is much faster than main memory, much faster than non-volatile memory, and so on. And some of these are very old and outdated, for instance, the magnetic tapes and the optical disc. And there are also some newer forms of technology that have come in that kind of transcend the boundary between storage media and main memory also, in case you're aware of. And think about what might be the equivalent of such a memory hierarchy on the GPU. This again will be addressed through the course, but if you're curious, go look it up after the class, right? This is on the CPU side. Think about what memory levels there are on the GPU side. Then coming to locality, again this is a very basic principle that you will find repeating in your maybe operating systems course, in your compar course, and even for the GPU architectures it is relevant. That's why I wanted to include this in the recap. So temporal locality refers to the fact that if an item is accessed, then the odds of it being accessed again are quite high. And whereas in contrast, spatial locality means that if you're accessing an item, then items at nearby addresses will be referenced soon. So spatial locality, for instance, you can think of maybe an array access, right? If you're doing a sequential read on the array, then that's a good example of spatial locality. You access the ith element, then you access the I plus 1th element, I plus 2th element, and so on. And this is something that can be optimized, right? That this is something that can that the operating system can kind of assume. So even when you access files from storage, right, the operating system caches some of that into what is called a page cache or a disk cache, assuming that if you access this location, you are likely to access the next locations also. And yeah, we went through the hierarchy, so I will skip this. One thing you need to keep in mind about the hierarchy is why are certain technologies at certain points in the space. For instance, what is the difference between main memory and some forms of storage? Okay, this is a question on temporal locality. Let's say you access A of I, and temporal locality means that you will tend to access A of I soon again. And see, both of these concepts of locality may not be universal. As in, I might have a workload that does not follow both temporal locality and spatial locality. There might be certain workloads whose access patterns follow spatial locality but not temporal locality, and vice versa. But these are assumptions that you can make so that in case the workload follows one of these patterns, at least then you will get the benefits of caching, right? Because think of it this way, the workload's access patterns will not be known to the caching algorithm, right? And you have to build a caching algorithm that is workload agnostic, that works across workloads, right? So what's the best you can do? You can make maybe these two assumptions and try to at least give a benefit to those workloads that satisfy these. And there might be some workloads which don't satisfy either of them, and in that case they will not get as much benefits of caching. And in fact, some workloads even manage for some workloads, right? So I'm talking about at the OS level. For instance, database access workloads tend to manage their cache on their own. They tend to write their own cache management algorithms and things like that. So that's also possible. But if you were building an algorithm that does not take into account the workload and tries to give you as good a cache hit as possible, then these are two assumptions that you can take into account about a workload. And for many workloads, this is beneficial, right? So it's one of those principles in system design: make the common case fast. So you can't address every single workload or every single access pattern, right, as a system designer. So what do you try to do? You optimize for the common case. So spatial locality and temporal locality can be thought of like that. You're trying to optimize for something that you think is common. Of course, there might be workloads where that is not the case. Is that clear? Okay, the person who asked the question left the meeting. I hope that was clear. Yeah, so what I was saying about the storage hierarchy right before this was think about why one particular medium is different from another one. And the answer to that is it depends on the kind of storage technology, the hardware itself, right? For instance, here's an example. Cache memory uses SRAM, main memory uses DRAM. Now, if you're curious, you can go look up these two and see why it is different. So we say cache memory is fast and main memory is slower. Why is that the case? That comes from the hardware and the kind of technology both of these use, right? So feel free to look that up if you want. So with that, I think we come to an end of the recap. So next I'll be spending, I think there were 2 or 3 discussion forum questions. So for people who have not seen them, we will briefly go through them here. And for people who've already seen them, there's nothing new here. I think all of them have already been answered. So this is just reiterating the same thing. Great. So the first doubt was on what are the reference texts to be used for this course. And I think the person who asked it wanted to know about one particular textbook or something like that. So these are the three textbooks that are recommended as reference texts for this course. And since I'll be sharing these slides anyway, they will be available to you. This answer is also posted on the discussion forum, so you could also get access to these names and these textbooks from there. But these are the official recommendations. And this is a standard computer architecture textbook, right? The Hennessy Patterson one. So I'm sure some of you have seen it and even read it. Going to the next one. So I think someone had a doubt on a question in the week 1's assignment, and this data is common across questions 1 to 3. So there was a typo in, I think, the question that was given to you guys. So please make sure you use the following data. And again, like I said, this slide will be shared, as well as this is already posted on the discussion forum. In case you have not seen it, please make sure to consider these changes before you submit the assignment one. So I'll just read it out. Will exam questions come out of the course videos? See, course videos are for you to get a basic understanding of all the topics in the course. The questions may or may not be directly from the course material, as in you might not get a verbatim question from the video. So it is recommended to read the textbook also for your own better understanding of a concept, right? But I don't know if officially what was told to you was to read the textbooks mandatorily. So I won't make a comment on that. I would just say that it would be good for you, and even for people who are preparing for GATE and things like that. Hennessy Patterson is a very standard textbook for computer architecture, right? So for instance, you don't have to read the whole thing, right? Topics that we cover in the course, make sure to go and look them up in the textbook and maybe read only those topics. That's a good way to break it down. But I would definitely recommend reading these textbooks and not relying completely on the course material. Okay. What is the role of the memory stage in pipelining? Because we fetch the instruction also in memory. From memory, instruction fetch also fetches the instruction from memory. Okay, I think I get your question. So this again, maybe this, I didn't mention this when I was explaining this, but it's there in your course videos. So not all instructions might have all of these stages, but this is kind of a superset of stages that you could have. So for certain instructions, like the load store instruction that involve reading or writing data from or to memory, the memory stage is involved. Not for all the instructions, only for these particular instructions. Whereas fetch is something that you would have to do for every single instruction, where you fetch that instruction from memory. Whereas the memory stage is different and it applies only to load store instructions. Is that clear? Great. Okay, so I think it would be helpful if I put more recap content going by the questions. So I'll make sure to have all of the course slides so that we can quickly glance through them, and if people have questions, we will pause there. Yeah, and finally coming to the third forum in the third question in the discussion forum, I think someone had asked about cache coherency and DMA. So we would be covering some of those topics in the upcoming course material. So by week 6, I think we would have covered some of the topics that are relevant to this question. So we will get back to the question after that. And we've also shared a link to a blog post that people can read if you're interested, right? So, great. So, I think that was all with the discussion forum questions. So, before we move on to problem solving, does anyone have any other questions on whatever was discussed so far? I'll also have time for questions at the end since it's a 2 hour session. So feel free to ask then or now. It's up to you. But I will wait a minute to see if anyone has questions. Great. So we'll take a break around 8 o'clock, a short 2 minute break because it's a 2 hour session and I said that that's a long time for people to focus on. But in the meantime, we'll get started with some of the problems. So a repeat for people who joined late, we expect the idea of having these live sessions is to make the problem solving very interactive. So all of these are designed as MCQs. So I will read out the question and then give you guys time to solve it. If it's a numerical, I'll make sure to give more than 2-3 minutes. And if you need more time, feel free to ask on the chat box. But please make sure you solve the problem during the live session and then post whatever answer you have on the chat box. So it doesn't matter if it's right or wrong. This is not an exam. So it just tells me about what you guys are confused about. For instance, let's say the right answer is A and a bunch of you post C, then I'll know that I have to focus on explaining why it's not C and why it's A, right? So it also helps me teach better. So please feel free to interact and ask if you need more time to solve the question. Ask if you don't understand the question very well, right? And these will definitely help you solve your assignment questions. They are very similar to those, so they will be helpful. Okay, let's get started. So here's the first question, and this data will be common from question 1 to question 3, very similar to what you guys have in your assignments. So let's read that out once. Consider a computer system with 32-bit memory addresses, 2K byte cache organized in a direct map manner with 32 bytes per cache block. Assume that the size of each memory word is 1 byte. Calculate the number of bits in a word field of the memory address. And your options are 5, 6, 7, none of the above. So since this is a numerical, I will wait at least 2 minutes. So take your time, solve it, and when you have the answer, please post it on chat. Okay, great. We have an answer from someone. A. Great. Okay, 5, which is also A. A. I'll wait another 30 seconds in case someone is still solving. A. Anyone else? Okay, I'm hoping everyone got time to solve the question. Explain the difference between word and block field. In this case, what would the size of the block field be? Okay. Yeah, I think that question is coming further down the line, but I will anyway explain each of those fields, right? So let's move on. So the answer is 5. I think most of you got it right, but let's look at why it is 5, right? And I want you to understand this beyond the math of it. So when it comes to main memory address, you can think of it as being partitioned into three portions, and there are different terminologies used for each of these things, right? So sometimes you might find it a bit confusing. So tag, I think, is pretty much uniformly used. The last portion, some people refer to it as word, some people refer to it as offset, and the middle one, block and line, as far as I know, are interchangeably used. So now think of why do you need these fields, right? So what you're trying to do here is have a certain size of cache and try to map your memory addresses to blocks in this cache. So I think you remember why we use blocks, because we don't want to have every byte being fetched, right? Having a cache block gives you the advantage of being able to fetch that much instead of going for a finer granularity. So the way you have things now is, in this particular question, you have 64 bytes per cache block, and you are also told that every memory word is 1 byte. So now think of this. What would you need to know given a main memory address? So one very common thing you can think of is which block of the cache does this address belong to. So this line/block is used for that. Then let's say that you're able to figure out which cache block this address maps to. Within that cache block, what exactly are you looking for, right? That comes from the last portion, the word or the offset. And the first portion, tag, is basically gives you a way to look up the cache and see if a particular um, memory block is present in it, right? Basically it tells you which main memory block is present in the cache, and this is relevant because you can have multiple blocks, multiple, maybe this should be corrected, multiple memory addresses that map to the same cache block. So this is kind of the conceptual understanding. Coming to solving this particular question, we are asked about the word field. How many number of bits does it need for the word? So remember again, the word or the offset tells you about where in the cache block the data, that the address that you're looking for is. It's like an offset, right? So think of this whole thing maybe as, maybe I already have the pen. Think of how you would describe a particular word in a book to somebody, right? You would tell them, go to this page, go to this line, and on this line, it is the third word. So this offset is kind of like that. You're saying, go to this particular cache block, and then you're telling which, in that cache block, which word or what offset is the data at. So now coming to, so I am stressing on the conceptual understanding because formula, I think, I'm sure all of you guys can do this, but it's also good to understand why we do something a certain way. So the block size here is given to us as, okay, right, I think there's a typo in this question too. I didn't notice it before, but the block size is given to us as 32 bytes, which is 2 power 5 bytes, and that comes out to be 2 power 5 words, since you're also told that one word is 1 byte. So then the number of bits in the word field that you need is 5, right? Because you can totally have 32 bytes, and you would need 5 bits to figure out where in that 32 bytes you're looking for. What is the offset you want? So that's why the answer is 5. Is that clear to everyone? Any doubts on this? Okay, there's a question. Since the number of blocks is not given, how would we calculate the bits in the block field? Great question, but I will go through the next question and answer before we get to that, because that's exactly what you're asked to do here. So, calculate the number of bits in the block field of the memory address. Go ahead and do this, and I'll again give you 2 minutes, and then we can look at the answer. Okay, cache line was 64 bytes. Let me just check that. I actually think there is a typo in this question. I'm sorry, I didn't notice it before when I was solving it. Let me just double check that. Yeah, I think I said 64 bytes per cache block, but it is 32 bytes per cache block. But feel free to work it out with whatever whatever initial data you noted down, right? The process matters more than the actual numbers. So work it out. If you've taken it down as 64 bytes per cache block, feel free to work it out that way. Okay, there's another question. Assuming it is a single block, 0 bits needed, you just need word bits. I'm not sure I understand that. Let me read that again. Okay, so if cache size is 32, then the answer is 6 bits. Okay, and if okay, got it. Anyone else who has an answer? Let me try to. Okay, great. We have answers to both questions. So good. That means you're understanding the concept. Let me try to parse this question again. Assuming it is a single block, 0 bits needed, you just need word bits. I see. So you think of it as a single cache block. But how would that really work, right? Because think of how many memory addresses you have. So I think we said it was a 32-bit system. And think of how you would be able to map that many memory addresses using one cache block. Is that possible? At least given how direct mapping works, is that possible? Okay, I hope everyone got time to solve this question. Okay, question mentions 60, let me read that again. 64 bytes per block, not the number of blocks in each cache line. The question mentions 64 bytes per cache block or cache line. That is right. Not the number of blocks in each cache line. I'm confused by what that means. So right, I think you have a little bit of a confusion on what the cache blocks mean, and yeah, so maybe I can do one thing. Today I don't have slides or content on direct mapping, and I think it would take me a good amount of time to draw the whole thing from scratch. So we can take this question up in the next session, where I'll spend 10 minutes, 5 minutes maybe explaining how direct mapping works, and I'll maybe clarify these terms and what exactly they mean, right? Because I am still not sure I understand your question very well. How many such 64 byte blocks would we have in each cache line? It's not very clear. So I think you have a confusion on the terms block, cache line, and things like that, right? So maybe look into it a little bit, but I'll also address this in the next class so that it's clearer for you. Or actually, what I can do is maybe add a slide after the session explaining what is a cache block, what is a cache line, and so that you can maybe understand it and use it to solve the assignment 1 itself. Okay, in the meantime, I see more answers. If cache size is 64, then answer is 7 bits. Okay, someone says if cache line was 64, then it's 5. If cache line is 32, then 6 bits. I see. Okay, cache size is 32, answer is 6 bits. Any other answers? And I will fix the typo before I upload the slides, so please take a look at it. I'm sorry about this. So I think the solution also might be for a different size, right? So what was mentioned earlier? Okay, we said 1 kilobyte. So let's just look through this, right? Regardless of what we said the question was. So let's assume that the cache size is 2 kilobytes. And in that case, converting that to bytes, you would get 2 power 11 bytes. So someone was asking, how do you get the number of cache blocks? So that is basically this formula, the cache size divided by the block size. So this is a very simple concept, I think. So your cache size in this case is 2 KB, and you're given a particular block size, right? I think it said 32 KB or 64 KB, doesn't matter. All you're being asked now is how many cache blocks are there. So given that you know the cache size and the block size, how would you get the number of cache blocks? You would just divide the cache size by the block size. In this case, again, we'd assume that cache size is 2 power 11 divided by the block size, which is 2 power 5. Again, I don't know if these match what you were initially told, but that's how you get the number of cache blocks. And given that you have 2 power 6 number of cache blocks, how many bits do you need to figure out which cache block you need to go to? So think back about this picture, right? This basically, you're trying to get which cache block should it go to. So how many bits would you need given that there are 2 power 6 cache blocks? So you would need 6 bits to figure out which block. So that's typically how you solve the number of bits in a block field question. And for people who solved with different assumptions, I'm sorry, that's perfectly fine. All you need to understand is the logic of how to do this. The actual values are fine. Depending on the question, they might change and your answers will still hold. So make sure you check for whatever values you solved with and see if you got the right answer. Okay, we are at 4 minutes to 8. So I think maybe it's a good time to take a break, or actually, let's finish the third question, which is um, going on with the same data. So, again, since there might be a typo and the question is shared for 1 to 3, there might be a typo here as well. But go ahead and do this with whatever assumptions you started out with. How many bits do you need for the tag field? And I'll wait 2 minutes, and after this question we'll take a break and come back. Okay, we already have an answer, 21. Anyone else? And take your time. Okay, someone else thinks it's 21 too. Okay, I think everyone has solved it. Does anyone need more time? Does anyone have a different answer than 21? Okay. If there's nothing else, then we can look at the answer. It is 21, and I'm sure typically this is how you guys have been solving these. So we look at the total number of address bits, and we were told it's a 32-bit address space, and you're simply told that the number of bits in the tag field would be the total number of bits minus the other two, right? So you have the block and the offset, and that was 5 and 6. So you subtract 11 from 32 and you get 21. So is there a way, I'm just curious to see, think about it in terms of the concepts, right? Like, what do each of these mean? Can you think of a way to get this without just doing this? This is kind of like a sanity check. You know there are 32 bits, so the sum of these three should add up to 32, right? And that's the fastest way there. It sure works. I'm not saying it doesn't work, but think about this, and you don't need to answer it right now. Think about it. How would you get the number of bits in the tag field without doing this subtraction? Think about conceptually what the tag bits mean and how you would derive that given all of this information. That's again a different way to get at the answer. It just makes sure that your concepts are kind of clear. So with that, I think we're almost at 8 o'clock. So I will give you the 2-minute break that I promised. Feel free to get some water or just walk around and come back. We will resume at 8:02. I think it's 8 o'clock. So we'll resume at 8:02. Okay, I think we can get started. Hope that gave you guys a, a chance to kind of reset and come back, and hope this is not too much. Okay, let's continue. So, again, this data is common for questions 4 to 8. So, let me read out the question. A non pipeline processor was redesigned as a 5-stage pipeline processor. The different stages have different latencies. The fetch, decode, execute, memory, write back stages have latencies of 400, 600, 500, 800, and 200 picoseconds respectively. Each pipeline stage incurs an extra 20 picosecond latency on account of the registers between pipeline stages. What is the cycle time of an instruction for the non-pipeline processor? So again, notice this part, it's asking you about the cycle time for a non-pipeline processor, not the pipeline one. So take your time, solve this, we will wait for 2 minutes. Any answers to this? Okay, 2500, great. Anyone else? I'll wait a minute more in case people are solving. Anyone else? Is the question confusing? Is the idea of pipelining clear to people? No answers? Okay, let's look at what the answer is. It is 2500. So why is it 2500? So, okay, not clear. What wasn't clear? The question wasn't clear, is it? Or is it pipelining? The concept of pipelining, is it clear? I see. Okay, the concept of pipelining isn't clear. Okay, got it. So, let's think about how do I explain this in an easier manner. Okay, let's take a very simple example. Forget about the 5 stages and things like that, right? This is just the concept of pipelining. And again, pipelining is applied everywhere from computer architecture to even software techniques, right? So let's say for the moment that you have two hardware units, maybe think of this as CPU, GPU, if that's easiest for you to think about, right? And now think that you have one particular workload that has to execute a certain amount on the CPU and then for a certain amount of time on the GPU, right? And now let's say I didn't do pipelining. I just executed this on the CPU. Let's say the CPU part takes maybe 50 seconds, the GPU part takes maybe 10 seconds, right? Now, and I have multiple instances of this workload. Let's say it's, I don't know, matrix multiplication with some pre-processing, right? Something like that. And imagine you have 10 instances of this workload. So WK1 to WK10. Now, one way I could do this is to run workload 1 first on the CPU, then on the GPU. And it finishes and it takes 60 seconds, right? And then after this, I again do the same thing with workload 2. I put it through the GPU and I put it through the CPU and then to the GPU. But think about this. In the 50 seconds that workload 1 is executing on the CPU, what is the GPU doing? Is it doing anything at all? In this framework of serial execution, it's not doing anything, right? It's idle. And when we think about hardware, we always want hardware to be well utilized, well used, right? If I have two hardware units on my system, I would get the best performance by using both of them as much as possible. Typically, there might be exceptions, but this is the general idea. So if something is sitting idle, then it's a bad thing because now the GPU is not doing anything and it potentially could be doing something. So now what I can cleverly do is when this workload starts executing on the GPU, the CPU is already free, right? So I can put my workload 2 to start running on the CPU, assuming that there is no relation between workload 1 and workload 2. They just follow the same patterns of CPU and GPU execution. So this is kind of the broad idea behind pipelining. So here in my example, I have two hardware units or two stages. So when the first one, and even though I said 50 and 10, I'm drawing them as roughly equal. So this is stage 1 and stage 2. So if you think of a timeline diagram, the workload 1 goes through stages 1 and 2, and then thereafter you have multiple workloads doing the same cycle, right? That essentially is the idea of pipelining, so that you don't have this idle time. You don't have this time where one hardware unit is just sitting idle waiting for its work to come in. And how does the instruction benefit from this? Now going back to our 5-stage pipeline, how does the instruction actually benefit from this? The instruction will still, think about the workload example that I gave you, right? If it takes 50 seconds on one hardware and 10 seconds on the other hardware, the total time for that workload is still going to be 60 seconds. So how am I really getting a benefit? The benefit comes because while this workload is still executing, you're already putting in another workload. So that helps you improve what is called the throughput, right? So remember when I explained pipelining, I told you, remember this one difference. Notice this one difference, that here we say in every clock cycle one instruction completes, but that does not mean that every instruction takes one clock cycle, right? And as we go through some of the further questions, this difference between how every we have one instruction, that is what you call as throughput, right? And how long does one particular instruction take, that is the latency. So this difference will get clearer to you in a couple of questions, but hope the idea of pipelining is clear. And going back from the toy example to our 5-stage pipeline, now think of it as those 5 stages, right? And when you don't have pipelining, which is what the question is asking you, this instruction has to go through all of the stages, right? And you are already given the time that each of these stages takes. So what you need to do is simply add up those times 400, 600, 500, 800, 200, and that comes to 2500. So that would be the cycle time of an instruction. So it basically has to go through each of these stages. Hopefully that was clear. Any doubts on this? Latency will come next, so watch out for that. That's fine. That I'm getting to, I think, in the next question or the next couple of questions, so don't worry about that. Okay, if not, let's move ahead because I think we have at least 5 more questions to get through. So yeah, so what is the latency of an instruction for the non-pipeline processor? Again, note that we're not talking about the pipeline case yet. We're still talking about the non-pipeline processor. So if you understand what latency means, try and solve this. If you have a doubt on what latency itself means, then wait a little, I will explain. But in the meantime, I'll wait for 2 minutes for people to solve. Any answers? Okay, so we have a definition for latency, duration for each instruction to complete, and 2500. Great. We'll wait a little more to see if someone else has a different answer, and then we'll talk about both the answer and what latency means. I think since the week one was kind of a refresher of computer architecture, for those of you who might be very new to computer architecture, some of these things might be difficult to understand. I realize that now. So I understand why there were questions on caching and pipelining basics. So from next week, I think it should be better because the material will be uniform. I think we'll be covering the same things in class. This was kind of a refresher, so I think lot of things are just quickly covered and you're expected to know the details. So I think looking up textbooks like Hennessy Patterson or even a standard course slide on some of these concepts will help you understand better. But I will also try to cover that gap specifically for the questions that were asked today. Anyone else? Any answers? Okay, if not, I think we waited enough time. So it is 2500 picoseconds. Right, and in a non-pipelined case, the latency and the cycle time are the same. It is the time taken for an instruction to complete. Okay, someone says 2520. Okay, where does the 20 come from? Okay, this 20 picoseconds. But this I think is applicable only when you have pipelining, right? It specifically says that the pipeline stage would occur an extra 20 picoseconds on account of the registers. So in the non-pipeline case, that 20 wouldn't come into picture. It is just 2500. So now coming back to the question somebody had about latency. Again, this is a very important concept, and notice that wherever I have slides that are outside what is covered from NPTEL, I typically have slide credits. You can click there and go learn more about these concepts. It's usually from some university's course, right? So feel free to look this up. But latency and throughput are terms that you will again keep hearing throughout your CS undergrad or masters, right? So it's important to understand the difference between the two. So latency is the time it takes to finish a given task. Throughput is the number of tasks you can finish in a given time. So we'll skip over some of these things, but the main thing I want you to understand here is through an example, right? So the example here or the task here is moving people 10 miles, and we look at two different examples here. One is a car and the other is a bus. So this car can seat 5 people, therefore its capacity is 5 and its speed is 60 miles per hour. Whereas the bus has a capacity of 60 but its speed is 20 miles per hour. And now we will discuss latency and throughput in this context. This is kind of easy for all of you guys to relate, right? All of us have traveled by a car or a bus, and we get this analogy of the capacity and the speed. The bus is typically slower, but it can carry a lot more people. The car is faster, but it can carry fewer people. Now think about latency. The latency is defined as the time to finish a fixed task. What is your task here? It is to move people 10 miles. So what is the latency of the car? Given that the car moves at 60 miles per hour, if you have to move 10 miles, it takes you 10 minutes. So that is the latency of the car. Now think about the bus, right? The bus moves at 20 miles per hour. So you want to move half of that, 10 miles, right? So that takes you 30 minutes. So now compare the two in terms of latency. The car has lower latency. As in, if you wanted to go from point A to point B, the car is faster, the bus is slower. Now think of throughput, right? The definition says number of tasks in a fixed time. And so how many people can you move in an hour? I think the fixed time here is an hour. So think about the car and think about the bus. So for the car, it comes out to 15 persons per hour, and for the bus it comes out to 60 people per hour. Again, work that out. I'm sure you'll be able to figure it out. But you get the difference between latency and throughput. That's the point I wanted to make. So throughput is about how many people can a bus or a car move in a given time. Latency is how long it takes you to get there. Now going back to this question, the latency is how long it takes for an instruction to go from the first stage to the last stage, right? Whereas if I asked you about throughput, think about how you would calculate. And now I have a question for you. You've learned about pipelining. Does pipelining improve latency or does pipelining improve throughput? Does anyone have an answer? If you understood this, I think you've understood the key idea behind pipelining. What are we trying to do with pipelining? Think about it and answer. Anyone? Throughput. Okay. Anyone else? Think about it. Take a minute. If you're new to these concepts, it will take a while to appreciate the difference, but I hope the example helped. Okay, if no one else has answers, yes, it is throughput. And if you think about it, right, does latency really improve if you pipeline? Does the time it take for an instruction to go from the start to the end change? No, it doesn't, right? So latency doesn't improve, but throughput improves. So I think someone said latency. So think about it. How does pipelining help with latency? If you think about one instruction at a time, because you pipeline, does it really change the time it takes for that one instruction to go from the start to the end? That's the key point here. And the other thing to notice, so you see that these things are in bold, right? So latency lower is better, because if you think about it as how fast can I go from A to B, Obviously, you want it to take the least amount of time possible. So the 10-minute is better than the 30-minute. If you think of it from a throughput perspective, how many people can I transport in an hour? Higher is better. So you can see that the car wins on latency and the bus wins on throughput. So that's the other point also that the slide makes, that latency and throughput are many times contradictory. And you can go through the rest of this sometime. I just put it because it's interesting, but yeah, you can go through it in your own time. I don't think it's directly relevant to the course. These are just key concepts that you should know as somebody, even if you're not from a computer science background. Anywhere in the electrical and computer science, this concept is useful to know. So I just thought we'd spend some time on it. Take some time to digest that, and if you're still not clear, if you're very confused between latency and throughput, get back to me the next session and we'll talk about it some more, because I think we are running out of time. So let's go to the next question. So what is the cycle time of an instruction for the pipeline processor? Now notice that we are talking about the pipeline processor, no longer the non-pipelined one. But the values of each of the stages stay the same. So think about it and tell me. We'll wait 2 minutes. $8.20. Great. Someone has an answer. Anyone else? Anyone else? Is this very confusing too? Okay, one more person says 8:20. Great. Do you need more time to solve this? Okay, we'll look at the answer. It is 8:20. Now let's look at why it's 8:20, right? So when you try to put in this 5-stage pipeline, you have to change the cycle time accordingly. And typically how this is done is the length of the longest stage is made equal to the cycle time. And I think this was briefly touched upon in the lecture video also, right? If you go and rewatch that, you'll see that professor was talking about how you can't clock it to the smallest one, then it'll be non-uniform, right? So you have to kind of pick the slowest stage and set the cycle time to that. And in this case, additionally, you were told that there is a 20 picosecond extra delay because of this register between pipelining. So how you now find out the cycle time is, how you find this out is you do the max of all of these 5 stages, because you want to find the slowest stage and accordingly set the cycle time. And additionally, you have to account for this 20 seconds, 20 picoseconds that it takes for the registers between stages. So that's how it comes out. So 800 is the slowest stage here. So 800 plus 20 becomes 820. And that would be your cycle time of an instruction for the pipeline processor. Any doubts on this? Okay, we have half an hour left, so I'll keep moving because I wanted to have some time at the end for any questions you had. So let's look at the next one. What is, again, same data, what is the latency of an instruction for the pipeline processor? Again, take 2 minutes, solve this. Anyone? We'll wait a minute more. Okay, 2520. Great. Anyone else? Anyone else? We'll wait for 30 more seconds. Okay, if not, let's look at the answer. It is 4100 picoseconds. Again, why is this? So understand this cycle time very well, right? So you're saying that I think the answer, whoever gave that answer, summed up each of the pipeline stage times and added 20 to it, right? But what now happens is that you're setting the cycle time to 820. And what the cycle time means, because all of these need to kind of be synchronized, meaning they need to happen in lockstep at the same time, right? So what you are doing is, even if this particular stage takes 400, by setting the cycle time at 820, you're making sure that that particular clock change will happen only at 820. So even though it is 400, it is going to take 820 now. Why do we do that? Like we discussed in the previous question, we are trying to accommodate for the slowest person, for the slowest stage, which in this case is 800 plus 20. So the goal is, when your clock changes, all the stages would have moved by one, right? You want that synchronization or that lockstep behavior, and that's why you're making it a point to set it equal to the longest one, the slowest one, which is 820, right? So now in essence what happens, it's like uniform, it's like making all the stages of the pipeline uniform, in the sense everything will now take 820 picoseconds, whether or not it was the same thing that was given to you. For instance, I think in this question it said something else, right? But because you're changing the cycle time to 820, everything will have to wait that long, right? So that means that your latency, or the time it takes for the instruction to finish executing, is 5 times 820, which is 4100. Great, you understood that. Okay. I hope that's clear. That's again a little tricky, but I think once you clearly understand what cycle time means, right? So in the non-pipelined case, it was simple because the latency and the cycle time were kind of the same. But in this case, the cycle time is being changed to accommodate the longest or the slowest stage. Okay, we will keep moving ahead. So, a CPI of 10 was observed from simulation experiments conducted with a perfect cache for a processor with clock rate 5 GHz. A 64 KB L1 cache having miss rate 4% and cache miss penalty of 60 nanoseconds is proposed to be used. What would be the CPI with the 64 KB L1 cache? 5, 8, 10, 12. Take 2 minutes, solve it. Any answers to this? I think this is one of those questions where you have a lot of data and you can't figure out which parts of it are useful to solve the question and which parts are not. Okay, we have an answer saying 22, I see. Okay, anyone else? We'll wait one more minute. Okay, the explanation for that is 300 cycles wasted 4% of the time. That gives 12 plus base CPI of 10. Anyone else? Okay, there's a question, CUDA based lab assignment source. I'm not too sure what you're referring to. Once we get to the lab assignments, maybe I can clarify that. Anyone else? I'll wait a few more seconds. Anyone? Okay, let's take a look at the answer. The answer says 12, and the way you get to 12 is with an observed CPI plus the penalty for a cache miss. So the observed CPI is with a perfect cache, meaning you always get a hit. Okay, someone else is getting 14, I see. And the penalty for the cache miss, which happens 4% of the time, with a penalty of 60 nanoseconds, which comes out to be 12.4, and the nearest answer that you have is 12. So I think there were a couple of different answers on this. So let me see. So I think I have your message on chat. I think I understand that you guys have calculated it differently from what has been given here. So I'll just verify the calculation and see if there is a mistake here or in whatever you guys calculated. And I will put up, when I post the slides later tonight, I'll make sure that the answer is correct. As of now, I think this answer is correct, but let's see. Yeah, I've copied your other answers, 22 and 14. I see 300 cycles wasted 4% of the time. So you're looking at the cache miss penalty in terms of the cycles. Okay, that's also a valid way to look at it. So yeah, I will address how you calculated this and see if it matches with this or not. I think I will do that offline because we have 20 minutes. Let's move on. So this is a very simple one. Dash type of computer architecture aims at reducing the time of execution of instructions. B, RISC. Okay. Anyone else? B, great. B, okay. This one seems to be clear for everyone. Let's look at the answer then. It is B, RISC, and I think this is kind of clear from the course lectures as well as the table that differentiates the two, right? So I'll skip over the explanation for this. And one thing I wanted to do, I think it was also mentioned in the class itself. Think about all the systems that you use today or that you hear being used, and think how many of them are CISC and how many of them are RISC, and think about newer technologies that are coming in. Just curiosity's sake, right? Think about how both of these have evolved. But yeah, let's move on to the next question. Mobile phone is RISC. Yes, very interesting. I hope you guys have also heard of RISC-V and things like that. Look up all of those things, right? I would always suggest try to relate to the course as much as you can. When you hear about these terms, the more you look at them as abstract things and try to just remember what the definitions mean, the harder it gets to really internalize what they mean, right? But the more you try to relate it with what you use and what you work on and what you see around you, it gets easier to absorb those ideas. So just notice all of these things. So say you learn about CISC versus RISC. Think about the systems that you use in your day-to-day life and think about, are they CISC, are they RISC, and in which case is RISC. For instance, someone said mobile phone is RISC, right? So why would your mobile phone choose RISC? Look at some of these features. What really makes RISC a good choice to use on the mobile phone. Are there mobile phones that use CISC? These are all simple things that you can do to satisfy your curiosity but also get a deeper understanding of the architectures. And once you make it that relatable, for instance, if you were to find out that one of these is more power efficient than the other, then you would realize that okay, fine, it makes sense to use that on my mobile phone because I'm not always plugged into a wall port having unlimited energy. Therefore, I should be conscious about how much energy I spend, right? Things like that. It will help you relate to all of these points that are just mentioned here. But moving on, a 16-bit address generates an address space of dash locations. Again, a very straightforward question. C65536. C. Okay. Anyone else? C. Great. I think that is pretty much clear to everyone. So it's just 2 power 16. We will leave it at that. Okay. So this is, I think, the last set of questions today. It's again on caching and it's very similar to the first set of questions that we did. I think the only difference here is that we use a two-way set associative cache. So I'll read out the question. We have a system with a 16-bit memory address and a 2k byte cache, which is organized as a two-way set associative cache, and it uses the LRU replacement algorithm with 16 bytes per cache block. Assume that the size of each memory word is 1 byte. Again, calculate the number of bits in the word field of the memory address. Four. Okay. Anyone else? Okay, 4. So I think solving that first question made this easier. A, which is 4. Great. I'll wait a few more seconds and we look at the answer. Great. Let's look at the answer. It is 4. I won't spend too much time here since we did a very similar question. So the block size is 16 bytes here, which is 2 power 4 bytes. And since you're told that every word is 1 byte, it also means that 2 power 4 bytes is 2 power 4 words. Now, how many bits do you need in the word field? You have 2 power 4 words, so you need 4 bits. Or very simply put, this word field or this offset tells you where in the cache block to look. The cache block size is 16 bytes, so you will need 4 bits to figure out that offset. That's all it is. Hope that is clear. Let's move forward. Calculate the number of bits in a set field of the memory address. Again, the terms might be slightly different, like I said, depending on the cache mapping, right? So here we use the set associative cache mapping. So think about it. I'll give 2 minutes for this since it might be. Okay, we have an answer saying C, but I'll give another minute for the rest of you. Take your time. Okay, you want the data? Great. Any other answers? Okay, 5. Anyone else? Okay, let's look at the answer in the interest of time. Number of bits in a set field. So the answer was 6, which I think some people said C. Let's see how you get to that answer. So the cache size was first of all 2 kilobytes, which comes out to 2 power 11 bytes. And you're told that it's a two-way set associative cache, which means that the number of cache blocks per set is 2. And now you, for the set field, you need to figure out how many number of sets there are. So again, the logic is very similar. You're given a certain cache, so you take the cache size. Only difference here, instead of doing just block size, which is what we did in the direct map case, because we were trying to figure out the number of blocks. Here we do block size into number of blocks per set, because of the way the set associative cache is, right? So here you're told that it's a two-way set associative cache mapping. Therefore, you multiply this by 2. If you were told that it's four-way set associative, then you would correspondingly change the multiplying factor. So this comes out to 2 power 11 by 2 power 5, which is 2 power 6. And once you get the number of sets, it is straightforward. You just get the number of bits as 6. So that's why the answer is 6. Is that clear? So you're basically grouping blocks together into sets. So instead of an address mapping to a block, now it maps to a set. And if it's a two-way set associative cache, it can map to one of the two blocks in that set. Okay, I am hoping that's clear. Let's move to the last question. Calculate the number of bits in the tagged field of the memory address. Anyone? Oops, sorry. Okay, C. Six. Okay. Anyone else? Six. Okay, I think that everyone got it right. So it is 6. So total number of address bits is 16. Number of bits in the tag field therefore is 16 minus the sum of the two, which is 6. So we'll skip over this. Oh, there's one more question. I think this is the last one. So this is a rather lengthy one. So a branch predictor is a digital circuit that tries to guess which way a branch will go before this is known definitively. The purpose of the branch predictor is to improve the flow in the instruction pipeline and play a critical role in achieving high effective performance. Let us assume that the series of outcomes of a particular branch when it was getting executed within a loop is given. Assume that these are the expected outcomes of the specified branch. There is a sequence given to you here, and T represents that the branch is taken and NT represents that it's not taken. Assume that the considered branch predictor always predicts not taken. What is the percentage of misprediction for the given predictor? So very simply put, forget about all this initial stuff about what a branch predictor does. Here is the sequence that a particular branch actually takes in execution. You have a very simple branch predictor that always predicts not taken. What is the percentage of misprediction for this particular sequence? Take a couple of minutes, work it out. Okay, we have an answer already, D, great. Let's wait for the others also too. D, okay. We'll wait another 30 seconds. So think of this as you predicting the outcome of something. Maybe it's a game or cricket match, whatever, right? Say that you always predict that a particular country loses, and here's the actual uh, set of outcomes that happened. This should be fairly easy to calculate, even if you know nothing about a branch predictor. It's okay. Everyone says D. Let's see what the answer is. Yes, it is D. So if you look at, so the branch predictor always predicts not taken, whereas you only have 1, 2, and 3 out of 12. The sequence length is 12, and you predict the right thing only 3 times of 12. So you predict the wrong thing the remaining 9 times, so 9 out of 12, which is 75% of the time. So that's your answer. Is this clear to everyone? Great. So with that, I think we come to the end of the problems, and let's see. So we have 5 minutes left. I think you guys have already stayed for too long hours, so I don't want to keep you beyond 9 o'clock. So what we'll do is, feel free to post any doubts or questions you've had on specific problems or some concept covered in week 1, and I'll make a note of those questions and address them in the next session. But use these 5 minutes to ask your questions. Any questions? Anything that wasn't clear? For instance, I think someone said they didn't understand hazards. So I'll talk about hazards the next time. But if there is something like that where you listen to the lectures but you are not sure what that particular term or that particular concept meant, feel free to just post a line here. I didn't understand XYZ, or could you please explain XYZ? I will definitely do that. Great. I'm glad it was useful. I hope you guys have. CUDA based lab assignment source. I'm not really sure what this means. I have only looked at the week 1 assignment so far. So maybe you can post this on the discussion forums, right? And the TAs will get back to you. Please do that. So I will stay around for the next 4-5 minutes. In case anyone has questions, you can ask, or if you don't have any questions, feel free to leave the session, and we'll see you next week at the same time. And thanks a lot for making it interactive, and I know 2 hours is a long time, so thanks to you guys for staying the whole 2 hours. You've had a lot of patience, and I hope you gained something from the long 2 hours that you spent on this. And if you have feedback on how to structure the session differently also, like I said at the beginning, feel free to leave it in the chat box, and I'll accordingly. Okay, I understand the question. I am not having a high-end system to practice CUDA. Any online labs will be provided? I have no idea on this, sorry. So please ask it on the discussion forum, and if they don't get back to you, I will make sure to find out and let you know. And the slides and the recording will be posted. Please look into the new CPI question. Which is the new okay, this 8th question that we did, right? Yeah, I think a couple of you had different answers. I will look at that. Right. Oh, okay. I think your question has been answered on how to practice CUDA programming. So the TAs and the instructors will be sharing instructions on how to use Google Colab to practice CUDA programming. So you don't need to worry about having a high-end system to practice CUDA. You will receive instructions on how to do that. That's the answer. I will clarify the CPI question for sure. So if there's a change, I will make a correction on the slides before I post it. Great. Anyone who doesn't have questions, feel free to leave the session. I'll hang around for a couple more minutes and then wrap up. Great. Thank you for attending. Okay, so this is the alternate method of solving the CPI question. Great, thanks for posting that there. I will look into that calculation. I kind of figured out that that's what you were trying to do earlier itself. So, yeah, I haven't worked it out that way. So, let me also try that out and see what's the correct answer, and I'll post it on the slides. Thanks for the question. Great. If there are no other questions, I'll see you guys next Monday at 7 p.m. Thanks so much for joining.